Previously, we introduced extractions as moving your solvent or moving your solute or analyte of interest from one solvent into another. So you might have drawn this going into another solvent. Okay, maybe going from a polar solution to a nonpolar solution because of the polarity of the analyte. Now, one thing to remember though is that this process is not complete and unidirectional. So when you have two solutions in contact with each other, the ability of a solute to dissolve, or an analyte to dissolve into one solvent, is the same idea as that solvent or that solute can go back to the other solvent. So this is actually an equilibrium where we will have a concentration in each of these different solvents. So there's a concentration of our analyte in our phase 1, which perhaps is the nonpolar, and an amount in phase 2 that's perhaps the polar. And these are at equilibrium. Now, what dictates if it's soluble, or which direction this equilibrium is driven to? What dictates whether it's going to be primarily driven to phase 2 or primarily driven to phase 1? And we know that this is due to the polarity, or the interactive or the attractiveness of the analyte to the solvent. Now, just like we describe other equilibria by some kind of a coefficient, whether it's a dissociation coefficient for like a Ka or a Kb, or a solubility coefficient, and that's like a KSP, here we're going to do the same thing. We're going to talk about a partition coefficient. Coefficient. I-C-I-E-N-T. There you go. Partition coefficient. And just like other equilibria coefficients, we're going to describe this with a value K. Now, this K term is equal to actually the activities of our analyte in each of the solvents. So our analyte in solvent 2 relative to the activity of the analyte in solvent 1. And so if we don't know activity coefficients, we can approximate this as concentration in each. Much like we would write in acid-base concentration, here we're writing our partition coefficient using the concentrations in each of the two phases. So what this is describing is the relative preference for our analyte to be in phase 2 versus phase 1, realizing that this is actually in equilibrium. Now, if we know that the combination of our analyte in each phase is our total analyte present, we have a total moles of our analyte, here S, or substance S, and I'm going to call that M here. Then we can describe this as the fraction in each phase as Q. So let's define this as the fraction of S in phase 1 at equilibrium. Okay. So if I define these two, then we can relate the concentration of our analyte S in phase 1 is the same as our moles times the fraction, total moles times the fraction in phase 1, divided by the volume of phase 1. And that would be the concentration in phase 1 there when we're at equilibrium. And similarly, we can do something similar to this for phase 2, but because we've defined Q in terms of phase 1, and this is a fraction, not a percent, so fractions are always less than 1, we can say 1 would be our total, that would be all of the analyte being present, minus the amount that's in, or the fraction of it that's in phase 1, which we said would be represented by Q, and divide that by the total volume for phase 2. So I now have these two expressions for my concentration of the analytes in terms of a total moles, the volume of each, and this fraction of the analyte in phase 1. So if I bring this back to my K equation and plug these values in here, we've got concentration of S in phase 2 divided by concentration of S in phase 1. Okay, and I'm going to solve for Q. Okay. Now I trust you to do the math here, and you're going to end up with a value or with a equation that looks like this. So I challenge you to do the rearrangement here, cancel things out, and you would get Q equal to the volume in phase 1 divided by volume in phase 2 times K plus the volume in phase 1. Okay, so when you solve for Q, you get this equation. So what does this describe? This describes the fraction of S in phase 1, which would be our original phase, at equilibrium. And this occurs after one extraction where we've taken phase 1, we've added phase 2, kind of shaken it up and seen where they come to equilibrium at. Okay, so we often call this an expression of the efficiency of the extraction. And so what does it mean to be very efficient? Well, we would say an efficient extraction is one where we have all of our analyte having moved to phase 2, or as much as possible, and very little remaining in phase 1, which means that a good or efficient extraction is one where this Q value is low, because that means that a very small fraction has been left in phase 1 and most of our analyte is now in phase 2. That would be considered a very good and efficient extraction. So we're looking for a small Q to say this is good. Okay. Now, when I perform a single experiment, is it better to just do one extraction using a lot of our extracting solvent, or to use some sequential extractions using much smaller amounts of solvent? Now, sequential extractions is going to take more time, a little bit more effort, but in terms of getting an effective or efficient overall extraction procedure, which one do you think is going to be better? Well, we're going to explore that topic next. But first, let's do an example using our equation for Q. Okay, so if you're following along and you haven't grabbed the separation efficiency worksheet yet, go ahead and grab that, as we're going to use that for these next couple of questions, and we're on question 3 in that handout. Okay, so our question asks, it says, suppose we have 50 milliliters of an aqueous solution of S. Okay, so I have my solution of S. I have a volume equal to 50 milliliters. Okay, and in this it says I am going to I have 50 milliliters of methylene chloride. Now this is an aqueous solution, which means it's in water. Oh, sorry, you can't see my thing. Okay, so we've got our S in a volume of 50 milliliters. This is an aqueous solution, and aqueous means we're in water, and so this is going to be very polar. I'm going to try extracting this with methylene chloride. And if you look at the structure of methylene chloride, this is a very nonpolar solution here. Okay, so we're told that we have a partition coefficient equal to 5. Now, thinking about what that partition coefficient meant up here when we first defined it, okay, A partition coefficient of 5 means that there are 5 molecules in S2, or in phase 2, for every 1 in phase 1. So what would this mean about the polarity of our compound? Well, it means that it's going to favor being in phase 2 here, okay, in that methylene chloride. So we're going to have our driving equilibrium being larger towards the methylene chloride than it is coming back to the polar water solution. So that means that our substance is much more of a nonpolar substance because it's favoring the methylene chloride, and we see that from our partition coefficient of 5. All right, so now we want to calculate the fraction of S that remains in the aqueous solution, or in phase 1, after a single extraction using a volume of methylene chloride of 50 mils. So this methylene chloride that I've added 50 mils of that. So to get our fraction remaining, we're going to use our equation for Q, which is the fraction remaining in S1, and we're going to use V1 is 50 mils, V2 is 50 mils, K is 5, and V1 is again 50 mils. If you plug this into your calculator, you should get a value of 0.16667, and that's the fraction left in solvent 1, or phase 1. Now let's say we only used 10 mils of methylene chloride. So our V2 now is only 10 mils. And let's say then our starting volume hasn't changed. So we're still using a starting volume of 50, but now instead of doing an extraction with a large volume, we're doing it with a smaller volume. How does that change our efficiency? Take a moment and guess whether you think our efficiency is going to go up or down, and then we're going to calculate it out. You can always pause this video and come back to it in a few minutes. All right, so to calculate this out, we've got Q equals, we're still going to put V1 in the top, that's 50 mils. But now V2, instead of being 50 mils, is 10 mils. Our coefficient has not changed, and our starting volume did not change. Plug this into your calculator and you should get an answer of 0.5. Okay. So what does this mean? It means that by dropping our volume, our efficiency drastically worsened, right? Because a lower number is more efficient. So it's more efficient if we're only going to do one extraction to use a larger volume in order to get the better efficiency. But what would be a perk of using a small volume then? Well, a small volume isn't going to have as much waste as a large volume, but what would happen if, let's say, we did multiple extractions? So we did a first extraction where we took our S in each phase and we extracted it between the phases, and then we removed this top phase and we took this bottom and we did another extraction where we took that same bottom phase 1, added some more of phase 2, extracted it, and now we removed the phase 2 again. And we repeat this over and over and over such that we're constantly taking the same phase 1 solution and removing subsequently more and more of our analyte by adding fresh aliquots of phase 2. What does this mean about the efficiency? Well, the efficiency Q for each extraction for extraction 1 is then multiplied by the extraction efficiency for extraction 2, times that for 3, so on and so forth, such that for n extractions, our our overall efficiency is Q to the N. Okay, so let's look at an example of that. So let's say we're continuing on with our S. Let's say we did 5 of these 10 milliliter extractions. My cords are in the way here. There we go. So we took this 10 milliliters and we're going to repeat this 5 times, where each time we're adding 10 milliliters as S2, and we're going to do this 5 times. N being our number of extractions, we're going to do 5. So what does this mean? So we would have Q to the N is going to equal our V1 over V2K plus V1, and we're going to raise this to the power, well, in the general form, N, right? Here we go. Our V1 is still 50. Our K is still 5. And let's see what our extraction efficiency is now that we're going to do 5 sequential extractions of 10 mils each. Okay. Q for the 5th extraction, okay, is going to equal our volume 1, which is still 50 mils, divided by 10 mils times 5 plus 50 mils. And we're going to raise all of this to the 5th. So this is the same as our extraction efficiency for one of them, 0.5, raised to the 5th. And we get a value here of 0.03125. So what does this mean in terms of everything we've done here? When we did a single extraction using 50 mils of methylene chloride, we got an extraction efficiency of 0.1667. If we use the same total volume of methylene chloride, a total of 50 mils, but we break it up into 5 sequential extractions of 10 mils each, now we have a much better efficiency, much lower fraction of the analyte left in phase 1, or only 0.03 of the analyte left. So only 3% is left here, whereas we left 16% of our analyte there. So in an ideal situation, what we want to do is to do a ton of tiny volume separations, especially if we don't want to end up with a ton of waste for a good separation, right? We can do these in increasingly small volumes, and we could do this on a scale where we're only putting in, say, 1 milliliter at a time and doing that 50 times. Our extraction efficiency would be even better than this. And so as we're starting to think about separations, we're going to base the next theory that we talk about in terms of chromatography in terms of doing essentially a series of tiny volume separations, one after another after another. And we do this in a way where we're going to consider having just a series of tiny separations. Okay, and we'll get into what that looks like and how we get to chromatography in the next segment. But for right now, keep thinking about how we're going to do multiple tiny volume separations.